inviting me and providing me an opportunity to give a talk. So, okay, so yeah, I'm gonna talk about the pollution sensitivity of bootstrap percolation, which is actually an ongoing project, which is currently fleshing out. So, okay, and I'm glad that I can talk about this. So, okay, let's get to introducing the model. So yeah, before introducing the model of the particular interest, I will first go over the classical and introductory widgets. So we're gonna first focus on something called the bootstrap percolation model. It is basically a cellular automaton in a grid G with two states. So one state is an occupied state, the other possible state is a vacant state, such that first, the update rules are monotone in the sense that the only vacant site can be changed to occupied site. Okay. Also, only the initial configuration is random. So usually each vertex, also called the site of the grid G, is initially occupied with probability P and vacant with probability 1 minus P, independently of all the other sites. So, and this is the only, source of randomness. And after the initial configuration is given, then, the update is kind of deterministic. So it is a random initial configuration plus deterministic dynamics. So yeah, this is first introduced by the Chalupa, Les, and Rage. I think they're physicists in 1979, and as a mean of studying, the Glauber dynamics. And so it is kind of the monotone version of Glauber dynamics. Okay. So yeah, let me first examine some examples. So one basic model or example of the bootstrap percolation is something called the R-neighbor bootstrap percolation, which is the bootstrap percolation in the hypercubic grid. And the vacant site becomes occupied if it is surrounded by R or more occupied nearest neighbors. So for example, in this case, we have two neighbor bootstrap percolation in a square grid. So these green sites represent initially occupied site, and the white, the site represents unoccupied site. So, at the next step, you see this site is surrounded by two occupied sites. So at the next step, it becomes occupied. And once they become occupied, they stay occupied for the rest of the time. So yeah, this is what happens after one-step evolution. For example, here, and many other sites will become occupied. Next step, we also have a bunch of sites which are surrounded by two or more sites, so they will become occupied. And if I keep evolving this configuration using the update rules, then eventually, in this particular example, actually all these square grid will be occupied. Okay, so that's one example. A slight variant of this model is called modified bootstrap percolation. So it is a bootstrap percolation in a square grid where the vacant site becomes occupied if it is adjacent to an occupied site in each coordinate direction. So for example, in the modified bootstrap percolation in a square grid where the dimension is 2, then each side will become occupied if it is surrounded by at least one occupied in each of the coordinate direction. I mean, both vertically and horizontally. So if I look at this unoccupied site, then because it is adjacent to this occupied site horizontally and this occupied site vertically, it will become an occupied site in the next step. On the other hand, unlike in the two neighbor bootstrap percolation, this site, although this is adjacent to two occupied sites, but they're both adjacent horizontally. So in this modified model, this site will not become occupied in the next step. So that's the difference. Okay. So in this case, I think if I run this dynamics indefinitely. Actually, let's see. Yeah, I think the eventual configuration is not fully occupied. So yeah, the modified bootstrap percolation is kind of more restrictive than the two neighbor bootstrap percolation in the square grid. All right, but yeah, is everything clear? Okay. Then, so yeah, in this model, what questions can be asked? So yeah, because it is one of the percolation model, one obvious question is whether there exists certain phase transition. Phase transition, one of the the prominent feature of many percolation models. So okay, let's formulate the question. So for a bootstrap percolation in a grid of a hypercubic lattice, how does the probability that every point of the grid is eventually occupied will behave as a function of P? Well, at least in the full lattice, when the grid is all of the the infinite hypercubic lattice, then it turns out that there are only trivial phases. So yeah, in the infinite grid, actually the answer is kind of trivial and not interesting. So okay, the result is that for R neighbor bootstrap percolation with R between 1 and the dimension D, or in a modified bootstrap percolation, for whatever positive initial density of occupied site, the probability that every point is eventually occupied is 1. So however thin, they will eventually engulf everything in the grid. On the other hand, for our neighbor bootstrap percolation with R greater than the dimension D, then for any initial occupied density less than 1, some portion of the grid will not be occupied, in the end. All right, and so let's see briefly see why this happens. So the idea is that the full occupation is actually initiated by something called the critical droplet. So it is some large occupied cluster in the initial configuration that grows without bound. So let's see what happens when we have some sufficiently large occupied cluster in the initial configuration. So say this is.
Sure, yeah. Could you go back to the previous slide?
Oh, sure, yeah.
The G is, can the G be bounded, just a finite?
We can consider both finite and infinite grid, but this result is formulated when the G is full, the.
Oh, okay. It's okay.
Right.
Yeah, I was thinking the result does not look correct if G is finite. Yeah.
Okay. I see. Yeah. Yeah. When G is finite, some the more interesting will happen, and actually we will get to the things very soon.
Okay. I see. Thank you.
No problem. So, okay, say this is part of my large initially occupied cluster, and say these are also initially occupied site. Then, okay, under the two neighbor update rule, see that this site, and therefore all this site in this say the first layer will be occupied. So why not use yeah. Oh no. Yes, so all these sites will be occupied because the growth will take place in both this and this direction. Then subsequently, this layer will be occupied, this layer will be occupied, and so forth. So as soon as this, sure, yeah.
Can I ask a question? So this picture you just showed me, like one of these legs, you've got the big green block, and then these, if there was one of these strips surrounding the green block that didn't have anything in it, it couldn't grow.
It couldn't grow, but if the cluster is already sufficiently large, then with a positive probability, all the other such layer will contain at least one occupied site.
Yeah, I get that, but the small, but if you get stuck at the beginning, it doesn't color the whole lattice, does it?
It might, but perhaps it might get in how should I say, the boosted by growth of other, the clusters. So actually growth, occurs everywhere, and they kind of grow by merging, the small clusters. That's the usual way they grow, but that usually, the full occupation is, mostly driven by, the already, large cluster.
Sure, that's clear.
Okay. So yeah, that's the way the at least the part of, this result is proved, or the idea is behind the thesis. Okay. So actually, I have some nice simulation, showing this. So yeah, let me see. Yeah, I think I can have the time to show this. So yeah, I coded this last night, and all right. So I think initial density here is 0.044 in the 600 times 400 grid, and if I run, this evolution, and you see the some part of the grid, so grow by first merging, the adjacent small cluster, but eventually they grow almost in a square way. So, okay. All right. So yeah, in the case of the infinite lattice, the answer was
sorry,
reverse. Sure, yeah.
Sorry, just so this growth is deterministic. So the answer could very easily be like not at all. But when you're looking at sort of the boundary of those clusters as they grow, do they have some sort of like I want to say scaling limit. I'm not quite sure if this makes sense, if it's deterministic growth.
Scaling limit.
Or yeah, they seem like kind of like a rough growing boundary, but it's some kind of deterministic process, which is a little weird.
So yeah, all the randomness are presented the initial configuration. So we randomly spread the occupied site in the initial configuration, and then run the dynamics deterministically. Yeah, is that actually what you're asking? Yeah. So not sure if some scaling limit might make sense, but there is certainly some the competition when you actually look at the finite grid and the initial occupation density, and that's actually something I want to mention in this slides. So if you instead look at the finite grid, say the d-dimension, the hypercubic grid of side lengths n, then there's some interesting phenomena occurs in the sense that there exists a p versus n scaling relation, which I'm going to represent by a function of both p and n, such that if p is sufficiently small and the size n is sufficiently large, then the probability that every point in that grid is eventually occupied as a function of this scaling relation function makes sharp transition from 0 to 1. In other words, if for a given p, if n is small, then full occupation will almost never occur. On the other hand, after a certain threshold, and if you look at the the grid of that size, then the full occupation will occur with high probability. So yeah, that is sometimes called metastability or the finite volume effect in this literature, but I think that is kind of the term borrowed from physics literature, and not sure if they actually have the exact the correspondence with that the metastability that physicists talk about. So okay. All right, so so that's the that existence of such p versus n scaling is something that's extensively studied in the literature. So for example, a classical result of this kind is the sharp phase transition result proved by Holloyd in 2003, which tells that if the lambda as a function of p and n is given by p times log n, so in other words, if I relate n and P by the relation that N is e to the lambda over P. Then in dimension 2, there's just a constant lambda star, finite and positive, such that if the probability of full occupancy converges to 0 if lambda is kept under that constant as P goes to 0 and N goes to infinity. And it converges to 1 if lambda is kept above that constant lambda star. Actually, the constant is even computed very explicitly. It turns out to be very sensitive to the the choice of objective rule. So for example, in the case of two neighbor bootstrap percolation, this lambda star turns out to be pi square over 18, which is actually 1/3 the zeta 2. Actually, the computation does involve the zeta 2 for some the very strange reason. And for the modified bootstrap percolation, it is precisely pi square over 6. In other words, if the N is kept below to the lambda star over P, then this will occur, and similarly for this one. Okay. So yeah, starting from this classical result, actually more general observation has been made. So it is studied for various update rules and in various dimensions. So for example, in 3 neighbor bootstrap percolation in dimension 3, it is proved by Valo and Bolovas and Maurice. And in our neighbor bootstrap percolation for any R between 2 and the dimension D is proved by these authors plus the Dominic Kuban in 2011. Okay. Also, there are many, other, related research. Recently, this is extended to a very general model called the U-bootstrap percolation, but let's not talk about that. Okay, so now that's something about the basic bootstrap percolation model, but the model I really want to talk about is something called the polluted bootstrap percolation. So what's the catch? I want to consider another type of sensitivity, which is that how does the presence of permanent obstacles affect the growth? So say we plant some permanent obstacles that is never occupied, but that also never affect the other side. In the presence of such obstacles, how will the growth of bootstrap percolation behave? So this model is first considered by Gravner and McDonald, and the description of this model is as follows. So each side in the hypercubic lattice is initially assigned polluted with probability Q, occupied with probability P, and vacant with probability 1 minus P minus Q. Of course, independent of all the other sites. Then, okay, so that's how we prepare the initial configuration. Then what's the dynamics? Well, the usual bootstrap dynamics is run on the the subgraph of unpolluted site. So we consider the subgraph only by looking at either occupied or vacant site, and that on that subgraph we can run the usual bootstrap dynamics. So that's the dynamics. So here again, I have an example. So again, let's consider the 2 neighbor polluted bootstrap percolation. So here the black side represent the polluted site or obstacles. And okay, so what will be, good example, right? So if I keep evolving this configuration, and then let's see, this polluted site prevents the growth, because this site can never become occupied. Okay. If without the presence of this the polluted site, first the growth will continue until this direction, and then it will fill this gap and it will continue to this direction. So this is actually preventing the growth in certain directions. Okay. Then, okay, now in this case, again, we draw a similar question as before. We will define two functions. The rho, which is the probability that the origin is eventually occupied under this polluted bootstrap percolation model. Phi is the probability that there exists an occupied cluster in the terminal configuration, where the terminal configuration is the configuration obtained by running this bootstrap dynamics indefinitely. Because the dynamics is monotone, the pointwise limit of the configuration is well defined, and that's what the terminal configuration means. Then in the paper of 1996, it has been proved that there indeed exists a certain non-trivial P versus Q scaling, the initial occupation density versus initial pollution density. So in the case of a two neighbor polluted bootstrap percolation in the square lattice, if we set lambda to be Q over P squared, then there exists two positive and finite threshold, lambda 1 and lambda 2, such that if lambda is kept below lambda 1, then the probability that there is eventually occupied is the probability that the infinite occupied cluster exists in the terminal configuration is 1 for P sufficiently small, and actually the probability that there is eventually occupied converges to 1 as P equals to 0. On the other hand, if lambda is kept above lambda 2, then yeah, phi equals 1 for P sufficiently large, and rho converges to 0 as P equals to 0. So that's the result that Gravner and McDonald observed. But of course, this gives a very natural question. Okay, so here we have these two thresholds, lambda 1 and lambda 2, but the question is, are they equal? In other words, does lambda 1 and lambda equals lambda 2 hold?
Excuse me.
Sure.
Is a scaling obvious intuitively? I mean, Q should be compared to P squared.
Yeah, we will have to get to that explanation later.
Okay.
So why we expecting this relation to hold naturally? So yeah, that's a good question. Yeah, that's very important. Okay. Well, actually, the proof technique they used is very far from resorting this question. So my contribution is that we can actually identify the nature of these two parameters. Unfortunately, the question of whether they actually equal or not is far more difficult than the other questions. So yeah. So anyway, let's state the main result of this talk. So for the same model, I mean, two neighbor of polluted bootstrap percolation in square lattice, again, if lambda is as before, then, well, the same result hold, but now I can identify the nature of these two thresholds, which is that they actually arises from another type of percolation model. They are, in fact, a certain percolation threshold of a continuum percolation model, which we'll define later. So we can transform the question of this strange and mysterious threshold to some percolation threshold, which actually fits into a very general, theory of percolation theory. Okay. Still hard to answer, but at least we have other way of studying that property of those threshold. So okay, let's get to the proof idea. Okay, so yeah, unlike in the case of basic bootstrap percolation model, the issue in the polluted bootstrap percolation is that it is very hard to track how the occupied cluster grows. So for example, let me actually Yeah. Run another simulation now. Polluted one. So yeah, polluted density is 0.002. Let's see. Hope you're lucky enough to see growth. So you see, for example, here the growth doesn't occur isotropically, but rather they are sometimes blocked by something until it is overcome by the growth from the the other directions. So it is quite non-trivial to track this growth in the polluted bootstrap percolation. Okay, so stop. Okay, so instead of directly tracking the growth of the occupied cluster, the idea is to look at, okay, what will the occupied and unoccupied interface in the terminal configuration will look like? In other words, what will stop the growth? So it turns out that the boundary of an occupied cluster in a terminal configuration has a fairly nice structure over. And moreover, that structure can be factually described only using the initial configuration. Basically, terminal configuration is very hard to work with because we actually don't know how it will look like. But instead, initial configuration is fairly simple. It comes from those product measures. So yeah, that's one idea. Okay, so the question is now, okay, I said that the boundary has fairly nice structure, but what structure we can discover there? Okay, turns out that the structure can be described most of the time fairly nicely, and moreover they actually admit certain scaling limit. So okay, so imagine that we run a polluted bootstrap percolation on some finite grid, and also in this picture I gave a certain boundary condition that both the left and bottom side are initially occupied. So the growth will take place in this northeast direction until they are hit by certain blocking structure. And as in this simulation, we see that those blocking structure usually look like some zigzag or the chain of certain wedges, where each corner is decorated by the polluted site. Okay, so I want to study this structure, and I want to, by describing the property of the scaling limit of this structure, I want to identify, study the growth of the occupied clusters. So, okay. So let's get into describing that blocking structure in more details. So as we saw in the previous picture, the blocking structure looks like they're formed by joining something called the blocking wedges. So okay, how will they look like? For example, let's consider this initial configuration. And then the growth will take place in northeast direction until it hits this the polluted side. And there, the growth is like a split into two directions until they encounter this another occupied site. And then there, only when it encountered that occupied site, now this structure will begin to collapse. So at least this structure can prevent the growth up to this point. But actually, this is not the only blocking wedge we can discover around the polluted site. For example, if I consider this slight variant, where the polluted site is not exactly at the bottom left corner, but it is slightly extruded like this, then it still can prevent the growth up to certain point. Again, by the nature of the two neighbor rules, yeah, it has to go all the way up to this occupied side in order that this wedge is destroyed. Okay. All right. Yeah. So now this also explains why we expect that scaling relation to hold. So okay, let's look at this blocking wedge. Then you see, basically, if I hold this an arm, then this arm, the length of this arm is a geometric distribution with parameter p, which tells that its typical length is of order 1/p. So in order that if it admits a certain scaling limit, then that scale the limit must be obtained by scaling the entire grid by the factor of p, and then in order for that this structure persist non-trivially, I must have that the number of such blocking wedges in that rescaled grid will be of order 1. So in the original grid, the number of such wedges will be on the average of order p squared. And that's the same as the pollution density. So yeah, we expect the pollution density to be p squared in order to expect some non-trivial scaling limit. So that's why we choose this scaling relation. Okay. So summarizing that we're gonna choose the scaling relation to be as a q equals lambda p squared, and then we're gonna discover the blocking structures in the initial configuration, and then you try to describe the limiting the scaling limit. So the question is, well, what will be the limiting object? In other words, what type of information we want to keep along the limit as p and q goes to 0? Well, certainly we want to keep both the information about the blocking wedges and their connective structures. In other words, we want to form another percolation model, where the grains are given by those blocking wedges and the connectivities are defined in a certain way. And then we want to now consider their limiting percolation model. Okay. So, right. So let's see how we might define the limiting percolation model. So in order to do that, I first need to describe the grains. Okay. So let's see what kind of the blocking wedges can be discovered along a polluted site in the polluted bootstrap percolation model. By the way, we are still looking at the two neighbor polluted bootstrap percolation because it is all the results are very sensitive to the particular updated rule we are using. So, okay, in this two neighbor PPP, okay, say this is a polluted site, then these are the 6 geometric arms that we can discover around this polluted site. Then, okay, basically the 3 different blocking wedges can be discovered. One, where the polluted site is located just below the bottom left corner. Second, the polluted site is exactly at the bottom left corner. The third, it is at the left of the bottom left corner. So, okay. And then connectivity of blocking wedges can be defined in a fairly straightforward manner. In other words, the overlapping blocking wedges of the same face can be joined together. And then they are together can prevent the growth of the occupied cluster from certain direction, at least up to a certain point. Okay. So that's the the percolation model we're gonna consider in the polluted bootstrap percolation site. Now, in the scaling limit of this, these geometric arms will become exponential arms. So, and the polluted side will become the Poisson point process in the plane. So the limiting object can be realized as a certain continuum percolation model, and that can be described as follows. So first, I'm going to consider a Poisson point process, the xi lambda on the plane with intensity lambda. This lambda is the same as the lambda in our scaling relation, and each Poisson point in the xi lambda, we're gonna define or attach 3 wedge-shaped grains, which is derived from the 6 IID exponential arms, just like how we did in the the polluted bootstrap population side. So I attach 3 vertical and 3 horizontal exponential arms, and I define 3 wedges in a very specific way, so that it the matches what we did in the polluted bootstrap populations. Okay. Okay, so it's a little bit weird way in which the grain arises, but that's how we're gonna describe the limiting object. Also, the connectivity is just the same as before. So yeah, the overlapping wedges will form a or considered to be connected. So for example, two regions in the plane A and B are said to be connected in this continuum percolation if there is a chain of the wedges that form a zigzag in this way and that connect from A to B. When that occurs, I'm gonna denote that event by this symbol. A is connected to B. Okay. Now we're ready to define the critical threshold. So one comes from the exponential decay regime of this continuum percolation model. So lambda 1, which is defined as the supremum of lambda, such that the probability that the unit this at the origin is connected to the circle radius r in this continuous percolation model decays exponentially as a function of r. So well, if lambda is small enough, and that is the case, so I'm taking the supremum of such lambda and defining that as my lambda 1. So in other words, in this graph, if lambda is any value between 0 and lambda 1, then the corresponding the continuum percolation model will exhibit exponential decay of the connectivity. Another critical parameter threshold is truncated long range regime, which is in the sense that, well, it is the infimum of our lambda such that the unit disk at the origin is connected to the circle radius r in xi lambda using only wedges of size r, size at most r. I'm not using the grain or wedges of arbitrary size, but only using size of r for some technical reason. And if the probability as r goes to infinity is positive, then I'm gonna call that the lambda is in the long range regime, and I'm taking infimum r such lambda and defining that as lambda 2. Usually in the percolation literature, they don't have this condition, and then they call, that's how they usually define this parameter. But unfortunately, we have to focus on this condition because working with unbounded grain in the percolation model is extremely hard. So this is some technicality that we need to prove. Okay, now the main theorem is that these lambda 1 and lambda 2 can be used as those lambda 1 and lambda 2 in the statement of the main result. In other words, if lambda is less than this lambda 1 defined as the exponential decay regime, then yeah, the probability that there exists an infinite occupied cluster in the terminal configuration will be 1 for p sufficiently small. But if lambda is above this truncated long range regime parameter threshold, then the probability will be 0 for p sufficiently small. Okay. So perhaps I'm gonna discuss very briefly about how the proof is done. So, okay, the first step is that we can couple the blocking wedges in the polluted bootstrap percolation to continuum percolation model. That part is fairly straightforward, but the caveat is that the connectivity structure can be only effectively related up to certain scale. After a certain scale in the side of a polluted bootstrap percolation, some I should call it pathological pattern will start to emerge, so that the interface between the occupied and non-occupied site in the terminal configuration is not effectively described by the blocking wedges. No. So I have to work at a certain moderate scale, but at least we focus on certain the range of a scale, then they can be coupled fairly nicely. Now using that, I can using the exponential decay of the connectivity in R, if in xi lambda, when lambda is less than that lambda 1, I can show that the blocking wedges are typically very short. The probability of having a long blocking wedge will be fairly small in this regime, and we can use that to show that it is very unlikely to form a large occupied cluster in the terminal configuration, because that will require that we have a very long blocking wedges or their connections. On the other hand, in the case where lambda is greater than lambda 2, so that the long range, we're in the long range regime, then the building up a very long blocking zigzag and therefore many blocking structure is very cheap. So yeah, we can effectively shield any possible critical droplet from growing up outside. So that's why in this regime we don't expect the infinite occupied cluster to occur in the end. So that's a very the loose sketch of the proof. But actually, do we have time? Yeah. Okay. So first, I'm gonna talk a slight bit more about the second part, how we might prove this percolating regime. Here, the percolating means that we can find an infinite occupied cluster in the polluted bootstrap percolation model. So in this case, again, the first step is that we can use the coupling between the blocking wedges in the polluted bootstrap percolation and the continuum percolation model. So using this coupling, that we can and together using the exponential decay of the connectivity in this continuum percolation model, we can show that the probability that some small the square is connected to a larger square of certain scale, scale of roughly order p to the -1 minus epsilon. That's good. Yeah, the factor rate. Epsilon. Yeah. Is converges to 0 as p goes to 0. So at least it is hard to connect, or it is hard to discover the blocking zigzag of this scale. Now, how we might use this observation to show that it is hard to, or yeah, that the infinite occupied cluster can be discovered. Well, so I'm gonna fix that scale that we are discussing in the previous lemma. Then we're gonna use some coarse graining argument. So we're gonna use this scale to and introduce the rescaled grid so that the, say, the box of standard at L times X of a side length L will be called good if we can find the blocking zigzag from square standard at that point LX and of side length L to the concentric square of side length 3L. Okay. So I'm gonna, if this is the case, then I'm gonna call this box good. Okay. In this case, now suppose that I have the square of side length 3L. Okay. And if this is surrounded by blocking structure, kind of the blocking zigzags joining together, then, for example, let's say this box will be good because if I look at this annuli, square annuli, then there is a zigzag connecting this smaller square to this larger square, so that this guy is good. So this guy is also good. So yeah, if such a blocking structure, encompassing this square exists, then actually in this rescaled grid, I can find the loop of good boxes. But we showed, using the result we observed in the previous slide, I can show that good boxes very hard to occur. The probability that a given box is good will actually converges to 0 as p goes to 0, which means that good boxes do not percolate. In other words, it is very likely that we can find the bad boxes that actually percolate from here to all the way to infinity. What does that mean? That means that in the terminal configuration, any occupied cluster containing this box cannot be bounded, or otherwise we should be able to find those blocking structure, bounding this box of 3L. Okay, so yeah, using that argument, now I can show that the infinite cluster actually occurs with positive probability, and that actually means that the probability of having infinite cluster is 1. Okay, so I think, okay, so I think I used over 50 minutes. So yeah, thank you.